Hello, my name is Akhil Dikshit and I'll be demonstrating our system CAvSAT, which stands for Consistent Answers via Satisfiability. It is a system for answering aggregation queries over inconsistent databases via SAT solving. Let me begin with some brief background. In the relational world, we define database schemas and a set of integrity constraints on those schemas. Common examples are key constraints or functional dependencies and so on. A database instance that violates the integrity constraints set on its schema is called an inconsistent database. For example, you could have a table employees where employee ID attribute is supposed to be a primary key, but for some reason you have two employees with the same employee ID 112, which makes this database inconsistent. In the real world, due to several reasons such as data integration, data warehousing, and in several different contexts, you could have these inconsistencies. In fact, inconsistent databases are pretty much unavoidable in the real world. Therefore, of course, we need to find ways to deal with inconsistent databases. There are primarily two approaches that are followed. The first one being data cleaning. It is the most common approach in the industry, and the idea is you somehow remove the inconsistencies from your data. You may add tuples to do that. You may delete some data. You may modify the values and update the data, but somehow you get rid of the inconsistencies and come up with a consistent version of your data, and then you evaluate your queries as it is normally, and then you get your answers to the queries. Well, this approach is more engineering than science because it often involves making some arbitrary choices. For example, if in a database, let's say you have two books with the same ISBN number and you want to clean the data, how will you decide which one to delete or which one to modify? That's an arbitrary choice that you have to make. There is another approach that's fundamentally different and arguably more scientific and principled, that's based on the notion of database repairs. And the idea is you keep the data, you keep the dirty data as it is, you don't clean it, but you handle all possible ways to repair the data at the time of query evaluation. So let me talk about database repairs and how it is used to give semantics to query answering. So this idea of database repairs was introduced by Arenas, Bertossi, and Homicki in 1999. And it says that, let's say you consider your database as a set of tuples, and you're allowed to delete tuples to make the data consistent, but you're allowed to delete minimal number of tuples. Yeah, you can't delete too many tuples. So every maximal consistent subset of your inconsistent database instance is called a database repair. Now, clearly, there is no single way to repair a given database instance. There could be many ways. In fact, there are exponentially many ways in general to repair a single database, is a single inconsistent database instance. Now, this notion of database repairs is used to give semantics to query answering over inconsistent databases. And this is called consistent answers. So the idea is, let's say you have a query queue. Now imagine on you have all your repairs of your inconsistent database, and you evaluate your query queue on each of these repairs, and then you'll have answers to your queries on every repair, and then you take the intersection of these answers, and then what you have is called the consistent answers to the query queue on your original inconsistent database instance I. The strong semantic guarantee that this approach gives you is that no matter how you repair your database, your consistent answers are going to remain the same. This is a nice pictorial representation of consistent answers. So as I said, you have one inconsistent database instance I on the top, the red colored one, and you have several repairs, J1, J2 through Jn, the green colored ones, and you have a query queue. You evaluate the query answers on each of these repairs. So you have queue of J1, queue of J2, and so on, and then you take the intersection, and what you get is the consistent answers to Q on your database I. Now, in the real world, queries often involve aggregation functions such as max, min, count, sum, and average. And they may even have group by clauses where you intend to apply the aggregation functions on groups of tuples and not the entire table, let's say. So in fact, select project join queries or SPJ types of queries involving aggregation and grouping actually cover a very broad class of practical queries. Now, the problem regarding consistent answers is that uh, considering the previous definition of consistent answers I just gave you, it's pretty unlikely that an aggregation query will produce any meaningful consistent answers. And this is because even if on two repairs, if an aggregation query produces two different answers, the intersection is going to be empty and you get no information, right? So for aggregation queries, the notion of consistent answers is extended by Arenas et al. In 2003, and that's called range consistent answers. So let me quickly tell you what these are. So now consider an aggregation query Q as shown here. So Z is the set of attributes we call grouping attributes. A is a single attribute on which an aggregation function F is applied, and T is a relation that could be expressed by an SPJ query, let's say. Now, a tuple T and a range GLB and LUB, which stands for greatest lower bound and the least upper bound, is a range consistent answer to Q on an inconsistent database instance I if the following three conditions happen. The first one says that on every repair J of I, there must exist D such that the tuple T comma D appears in the query answers on that repair, and D falls within the range GLB and LUB. Okay. The next two conditions simply say that this range must be tight, meaning that there must exist a repair such that T comma GLB appears in the query answers on that repair, and there also must exist a repair on which a tuple T comma LUB appears in the query answers on that repair. Let's quickly go back to our example. You have an employees table with tuples 2 and 3 violating the key constraint. Now, on the right hand side, you see that there are two repairs that you can do on this instance. The first one is a repair by deleting the third tuple. So you just keep tuples 1 and 2. And the second repair, R2, is when you delete tuple 2 and decide to keep tuples 1 and 3. Now consider an aggregation query where you want to select a role and the number of people having that role. So select role comma count star from employees group by role, right? And as per the definition above, we see that the range consistent answers to Q on this database instance I are the following. It tells you that no matter how you repair your data, you are guaranteed that you will find at least one software engineer and at most two software engineers. Similarly, there exists a repair on which there is no software intern, and no matter which repair you pick, you're guaranteed that you will find no more than one software intern. These are the range consistent answers. Now let's talk about the complexity of computing range consistent answers. So even for a fixed SPJ aggregation query, computing range consistent answers over a database instance that violates just simple primary key constraints is also in general, I mean, it can be in general a computationally hard problem, an NP hard problem. And because of this, there are not really many systems. In fact, there is only one existing system that does compute range consistent answers on the real world databases, but that is also based on an approach called query rewriting. So it applies to a very small set of queries. Okay, and this computational hardness is probably the reason why uh, the approach of consistent query answering and range consistent answers is not widespread in the industry today. But here comes the distinctive feature of CAvSAT. Uh, in CAvSAT, we have SAT solving modules, and they implement several reductions from range consistent answers to variations of SAT. SAT meaning a very well-known NP-complete problem of Boolean satisfiability. So what we do is we take this database problem of computing range consistent answers and reduce it to variants of SAT, SAT or one of its variants, and then deploy suitable SAT solvers to compute the optimal answers. Okay. So these reductions depend on the aggregation functions present in the query and also whether the query has group by clause or not, and so on. And we have these different reductions. We also have different methods. So for example, for some queries, let's say if the query contains a group by clause, you need an iterative method because for each group you need to compute the two bounds and so on. And these instances therefore can have both hard and soft clauses, right? And of course, as I said, after reducing this problem, after constructing a SAT instance, CAvSAT deploys a suitable solver such as glucose or max-HS to compute the optimal solution. And then these solutions are translated back to the range consistent answers to the query. For now, CAvSAT supports SPG aggregation queries involving some count of a particular attribute or count star aggregation functions with or without grouping. We are currently working on max and min functions. We have an approach to compute answers, but that's quite slow compared to these three. So for now, we are demonstrating only sum and count of an attribute or count star functions. Now, let me talk about the architecture of CAvSAT. So we have a modular architecture, and if you see, start on the left, we have a query preprocessor module. It takes the input query and the set of integrity constraints and attempts to determine the complexity of computing the consistent answers to the query. As I said, there are some queries for which the consistent answers are rewritable in SQL, meaning that the problem is not NP hard, but you can actually compute the range consistent answers within the database engine itself. And if we know that the input query is of such type, we forward it to the query rewriting module that implements several query rewriting techniques from the literature. But of course, not all queries have SQL rewritable consistent answers. So if the query doesn't belong to this type, then it's forwarded to one of the SAT solving modules, depending on whether the query has aggregation functions or not. And then the SAT solving modules implement these reductions, deploy SAT solvers, and compute the consistent answers. For this demonstration, we have implemented the system. If you look in the middle, we have implemented the backend of CAvSAT as a Spring Boot application, and we deploy it on a web server. It, of course, has access to powerful SAT solvers or solvers that can solve variants of SAT. For example, weighted partial max SAT, as it's shown in the diagram, WP max SAT. One such solver is max-HS. The data is stored in a traditional database management system such as Microsoft SQL Server, or it could be Postgres, MySQL, or any database management system of that sort. We of course need to store the set of integrity constraints. And then on the user interface side, the UI is web-based, and we have implemented that using React.js framework. With this, let me jump to the demonstration of CAvSAT. To begin with, the user of CAvSAT joins, it logs in with simple SQL Server authentication. So as you see, I'm connected to an SQL Server at localhost. The user gets to select a schema. So for this demonstration, I'm choosing bank accounts schema. If you go on the preview schema and raw data tab, you get to see what tables you have in your data, and you can preview some rows in each table. If you click on the constraints, you get to see the integrity constraints on this database. For example, ACCID attribute is a primary key in the table accounts, and so on. And remember, this database is inconsistent, so it may not follow these constraints. It may violate these constraints. To begin with, let me bring one SPJ query where, let's say I want to find out the names of the customers from these three tables. names of the customers where uh, the customer belongs, I mean, the customer has an account that belongs to the same city as the customer. Okay, so this table has a join between these three tables. When I execute, uh, I see that John is a single consistent answer. Okay, but if I execute this query directly on the inconsistent database, I get what's called as potential answers, and I see there are two more rows, and these are not consistent answers, meaning that there exists repairs such that these two rows don't exist in the query answers. That's why the only consistent answer to this query is actually John, and it's computed via partial max-out solving. If you look at the query analysis tab, you get to see a visual representation of what's known as attack graph. It is constructed from the query and the set of integrity constraints. And the properties of cycles in this attack graph tell us about the complexity of computing the consistent answers. So this attack graph has a cycle between these two tables, account and customer. And this tells us that computing the consistent answers to this query is in fact co-NP complete. Now let me uh, get an aggregation query. So let's say we want to find out the sum of account balances that belong to a customer named Mary. Now we have an aggregation query, so we expect range consistent answers. So CAvSAT has returned us the range, that's greatest lower bound and the least upper bound, which is 900 to 2200, guaranteeing that no matter how the data is repaired, the sum of account balances of Mary is guaranteed to be between 900 and 2200, and this range is in fact tight. And finally, let me take an aggregation query that involves grouping as well. So for example, you want to find out the number of accounts that exist in each city. This can be written as select accounts.city from account star from accounts group by accounts.city. When I compute consistent answers, now for each city you get the range. So for example, for Los Angeles, both bounds are 2, meaning that in every repair there are exactly 2 accounts in Los Angeles. But for the city of San Jose, there exists a repair in which there exists only 1 account in San Jose, while there also exists a repair in which there are 2 accounts in San Jose, and it's also guaranteed that in every repair, the number of accounts in San Jose, it's either 1 or 2. I mean, between 1 and 2, which is either 1 or 2. With that, let me go back to the presentation. I would just like to end. We have the code of CAvSAT available on the GitHub repository uccross/CAvSAT. We have open sourced this code via a BSD style license. And with this, I think I will end my demonstration, and thank you very much for listening.